All right, thank you. Welcome, everybody. Thank you for coming. It's a pleasure to have here today Dr. Harry Chang from the U.S. Army Research Office. And Dr. Chang received his degrees, his MS and PhD from the University of Rhode Island in mathematics in '74. He's had a very full and fruitful academic career at the University of Alabama, where he's started several and initiated several programs, research programs, and he's also worked at MIT in the Lab for Information and Decision Systems. He's graduated, I guess that's the job of any academic. He's graduated numerous PhD students, and more recently, I understand 5 years ago, he moved to North Carolina, beautiful North Carolina, where he joined the research program at ARO, where he's program manager there for the probability and statistics program. And today he'll be talking about optimal delay control of stochastic systems with memory. And it's a pleasure to have you. Thank you for coming.
Thank you for inviting me. What I'm going to talk about today is actually the result of staff research at the math department in this university. My joint work with Tao Pang, maybe some of you know him, maybe not, and also a postdoc. He used to be a postdoc, Mustafa Pemi, but he got a job, tenure earning position to Maryland, so I lost the postdoc. So right now, just Tao Pang and I are working on the problem. And this talk is going to be based on a paper with the title of optimal control of stochastic functional differential equations with bounded memory. And the paper is going to appear in the journal called Stochastic, and it is an international journal for probability and stochastic processes. So, this is the outline of my talk, and essentially what I'm going to do is that I'm going to consider a system, control system, which means that there will be a control stochastic differential equation of some type. And your control process is U. It's a stochastic process. And you can treat that initial condition, initial data as your input. You should also treat the control process as your input as well. And then through the dynamical process equation that you have an output. However, this equation, the equation that describes the control stochastic differential equation, will have a delay in the state variable. Well, for example, why the state delay? For example, one simple example is that was today the coldest day in the winter so far? Yes.
It's supposed to be.
It's supposed to be, yes. In the morning, you were, in a hurry to rush to work. You jump in the shower, you turn on the water to the hot, and you thought you're going to have a hot water. The answer is no, you're going to have a cold water for a few seconds, right? So there's a delay in there. Okay? So your state variable has a delay. Now, my title have an optimal delay control. I would also look at the situation where not only that you have a state delay in the state equation, but as well as in the control. And I will show you some examples to see what kind of situation that you need both state and control variable have a delay term in there. Okay. So I will start with the important thing about this is to do it correctly. I need to have a right notation, and so the first thing I will look at it is to introduce some notation, and then I will give you 3 examples, and thereafter, I will look at a very general control problem, and I'll formulate it. I will define what is optimal control and what we want to do in that control problem. And I will use the dynamic programming principle, which many people knows. It's a Bellman type of dynamic programming principle. And from there, I will show that I will show you that the value function of the control problem in the continuum satisfy an infinite dimensional Hamilton-Jacobi-Bellman equation. And of course, this equation is quite different from any other equation you may have encountered. Usually you say, oh, I will encounter partial differential equation, which is hard enough. But this is some kind of equation that will involve Frechet derivative, because we are going to work in an infinite dimensional function space. And so then the question is, what does it mean by a solution? And so forth. So I will explain that we will not be able to expect that the equation will have a classical solution. The classical solution means that you have a function that is differentiable up to whatever derivative involved in that equation, and is smooth. But in fact, in most of the control problem, you don't expect that it has a smooth solution. So then we'll look at some so-called weak solution. And this weak solution is in terms of a viscosity solution. In fact, viscosity solution for regular PDE started sometime 20 years ago, and the work was supported by ARO. During that time, there's a mathematical research center at University of Wisconsin. Later on, it was closed down. You remember back in the Vietnam War, that there was a group of students who, kind of try to get that Army Research Center out of their campus. But it wasn't closed. But later on, there's quite a few very good mathematician, PDE person, who started the so-called viscosity solution. But my equation is a lot more general than that. And I would perhaps don't have time to illustrate that. I will mention that the value function turns out to be a unique viscosity solution.
Excuse me, could I just flip your mic to the outside of your shirt, please?
The mic, please.
Yeah.
Oh, this one here?
It's clipped.
Oh. Oh yeah, clip to it. Oh yeah, okay, sorry. Oh, this one.
Yeah,
oh, I see. Should be here, closer.
But it should be also directed up.
Oh, I see. All right. So, can you hear me now?
Oh, yeah, it's much better, thank you.
Okay. All right, the one notation that is important is that I'm going to look at the situation where you have a bounded delay, which means that your delay will not be infinite. And your system sometimes will depend on the state R, unit of time ago. So this R is your delay, duration. So I'll be working on a space of continuous function that is defined from the closed interval negative R to 0 into Rn. Okay, and I will call this space script ball phase C. And of course, this is a function space, right? We are looking at the space of all continuous function that is defined from the time interval from negative R to 0 into Rn. And I like to equip this space with some topology. The topology, I'm going to equip this with is the so-called uniform topology or the soup norm. So take a continuous function defined from negative r to 0. You want to see what is the magnitude of this function. Is you take an absolute value, which means that wherever is negative, flip to the positive side, and you look at the highest point of the line. That will be your norm, where in the vector in Rn, you look at the how long that the vector is. But in the function space, this is the measurement of the vector. Okay, and we know that the C is an infinite dimension. In fact, it's a Banach space under this topology. And this Banach space is harder to work with, although it is quite easy to visualize what kind of function we are dealing with. Because this Banach space does not have a system of orthonormal basis. There's no basis that you can work with to say, all right, I take any vector in that space and it can be approximated by a sequence of orthonormal basis. It won't happen, okay? But however, I'm going to look at a bigger space, which is L2. L2 is the space of all the square integrable function, the Lebesgue integrable. And if you are not familiar with the Lebesgue integral, you can treat it like a Riemann integral if you want. Okay, in some cases, it's more general than the Riemann integral. And so this is an inner product, right? This is an inner product that we normally use. And I'm going to call the norm as a L2 norm with the subscript 2. And it is known that try to look at the space C, which can be embedded into a bigger space L2. And in fact, that it can be embedded continuously in terms of, remember we are looking at the soup norm, we are looking at the L2 norm, and because of a difference in norm, you can embed it in there. So you can treat every continuous function as a L2 function, sure, right? Okay, now this is these three bullets represent a very important notation. And here, I'm going to make distinction between psi of t and psi sub t. And let me draw it on the thing here. I guess I can draw it on this, right? All right. So that for example, here's negative r, here's capital T. You have a continuous curve, right? Now, if I were to say, given a small t, you look at this is your psi of t, okay? Just like, the regular notation. However, I want to say that if its psi sub t would be this piece of curve, this is your psi sub t. Okay, so there's a big distinction between psi of t and psi sub t. And why is this important? Right? This will show up in the equation, in the very general equation.
You have to put the pen back.
Oh, pen. Oh, I see. Ah. Okay.
Just to make it complicated.
All right. Why do we study control system, a stochastic control of the delay equation? Well, I just mentioned a little bit earlier that the external force on a system, the reaction to this external force is never simultaneous, right? Have you ever seen any simultaneous reaction? There's always a delay. It takes time. So whatever your reaction to the external force is depending on r second or nanosecond earlier, right? So there's never you never have any instantaneous reaction. And because of that, we have the delay equation. And this is one example that I want to show you. And of course, I'm in the business of funding basic research, and I thought this example is quite appropriate. Now try to think of it this way. Why a certain country is very advanced in scientific advancement? Why? Because there are research money, especially in basic research, poured into it. Okay? And also the level of scientific advancement depends on your current level of scientific advancement, as well as in the past history. There's certain history that you have to carry over, right? It's not just depending on the current scientific advancement level. And of course, when I say you need to put in the money investment into it, the advancement, the rate of increase in the advancement doesn't depend on the investment at this point. It might have previous history you have to take into consideration. Well, take basic research, for example. Let's say you got an NSF grant. NSF grant give you money, but you cannot say, oh, my research level increase instantaneously with respect to the amount of money you just received. It depends on how much you have received in the past, because there is a time delay, right? There's a certain work you need to do, right? So these are the control delay, right? So look at this equation, that y of t is the level of scientific advancement, and you can say it's a competitiveness relative to another country. Either way, you can interpret it. And now this is a instantaneous increment, depends on the current level, as well as a weighted average in the past from negative r to 0. So this will be from negative, from s minus r, taking a weighted average by this a sub 1 function to s, to the current time. And not only that, it depends on the current funding level, as well as on this average historical funding level, right? So look at this. This term, the second term on the right, depends on the history of the state in the past. And the fourth term here depends on the history of the funding level, right? And now I have a randomness added to it, which means where it's not really for certain that research team receive certain money will yield deterministic result in research. There's always some uncertainty. And this term is your uncertainty. So you see, you have an equation, the control system equation, where the control equation has a delay, depends on the past history in the state, as well as depends on the past history of a funding level, a control. Now, in this particular problem, in order for this equation to make sense, is that you need to know the initial level of scientific advancement. So let's say your time starts from 0. That's the initial time. You need to have some history, okay? And this history will be from negative r to 0. It's your continuous function. You also need to know the historical funding function, okay? In order, by having these two initial conditions at the time 0, then you can say, all right, and also the funding input, then you can say my output is y of t, and from t from 0 to whatever time. Okay. And then as I said, that the U is a stochastic the control process, which should be adapted to the system itself. To means that whatever happens, the controller have a complete observation. Of course, there are situations where you have incomplete observation. That will be different type of problem, but that's more complicated problem. But here, let's make it simple. And so that those coefficients, A0, the first term is non-positive, which means if you do nothing, no investment, your scientific advancement or competitiveness will go down, decrease. That's why y dot equal to A0 y, right? And A0 is negative. And this A1 is a weighted function and so forth. So I don't need to, all these coefficients have a certain explanation. But again, that I did say you need to have an initial state function, not just one point, one vector, but a historical function. You also need to know historical initial investment. And so that what is the purpose of all this? You want to choose your control process so that this expected return, the research return, is maximized. And when I say the research return is, you have a utility function of, at the end, capital time, t. You want to maximize the utility function of this, some function of advancement. On the other hand, you don't want to overspend your money, right? You want to minimize your expenditure. But here, I want to maximize the total thing. So you need to put a negative. When you have a maximizing negative, is equivalent to negative or minimizing. And L is a utility function of your expenditure. Okay, so you want to, and of course, cap psi and L are some utility function which satisfy certain conditions, which come from economic theory, utility theory. So you want to find your U admissible control so that you can maximize this expected return. All right, so this is one problem with, solid problem. Now the second one, I guess here I know many faculty are in the communication networks, and this is based on a joint paper with Bob Boogie, who is in math department. Boogie also, he came from Brown University. In 2002, he was Harold Kushner student. Okay, Harold Kushner, he got his PhD. Harold Kushner wasn't a mathematician to start with. He was, I believe he got an engineering PhD from Wisconsin, long time ago. And then he joined Brown. He's a faculty in applied math. And his specialty is looking at the heavy traffic approximation of communication network. And so for convenience, Boogie in the math department here, we got a chance to talk, and I try to sell my idea about delay, how important the delay that you need to take into consideration. So we work together, and the paper appeared in a proceeding, I think it's a 2005 proceeding of Control and Decision Conference, IEEE. So this is what we do here, that you have a mobile system, K of those, that people have a cell phone, K of those guys, and assuming moving around. Each of those channel, the state of a channel, the condition of channel changes with respect to time. So you have this J of S is a stochastic process which is of capital K dimension, and this vector value process is a stochastic process and change with respect to time. And for convenience, it should be a semi-Markov, but you can also consider for ergodic process for whatever reason, whether it's realistic or not in communication, that doesn't matter. But in each of those channels, I have an achievable transmission rate, which means per unit of time, per unit power, that you can transmit how many packets and so forth. And it depends on that the condition of the channel, right? J. So it's a function of J. Now, in the heavy traffic, loosely speaking, you would say a system is in heavy traffic situation if no processor is idling. So they are quite busy. So they are operating close to its capacity. So loosely speaking, it means that. And mathematically, it means that that the arrival rate is balanced with this departure rate, expected departure rate. So they are quite, arrival and departure, they are balanced. So that means nothing is idling, right? So they are quite busy. So mathematically, you will interpret it this way. And Kushner's work, which and along now, many mathematicians or even communication engineers, they are interested in so-called diffusion approximation of, normally discrete state type of network. For example, the arrival rate may be Poisson, and although some people would look at the heavy tail type of thing, but Poisson has a discrete state value, right? And so they use a continuum, so-called diffusion approximation, and try to write the Q size, X of S, which is the Q, the number of packets waiting at each of those nodes, which we call X. And this Q size is the description of network traffic. And you can use some kind of a diffusion approximation to write it as a stochastic differential equation. And let me explain what this is. This is an initial Q size in those nodes. And you have a drift term. Now, it turns out the result we got is that if you know a packet in the communication system, there are delay. What are the delay? The transversal delay. It takes time for the packet to go from one place to another. And in another delay is sometimes you need to send the message back to the sender to say, oh, I have received it or not. But sending those things take time. So your knowledge of the state system is not current. It depends on the delay state. Okay, and this, of course, is a noise term. Again, that the Poisson process go through the continuum approximation will become a Brownian motion. And why you have another term which is called refraction. We all know that the Q size never go to negative, right? Because that just doesn't make sense. Either it's zero, nobody waiting in line. You cannot say negative number of packets waiting in line. So every time one node, the Q size at certain node is zero, there will be no chance of going further to the negative. In fact, it may become bounce back to positive if there's a new arrival. So this Z of S term is a refraction term. And so this equation, we can say, is a delay stochastic differential equation with the reflected term. Okay, and in mathematics we call this a Sklar-Rotherhard stochastic differential equation. Now, without this term, we will just say stochastic differential equation. And here's a delay. Now, what is this B? B turns out to be, depends on your transition, your control, transition rate, the sending rate, which depends on the condition of the channel as well as the current state X, and also depends on your departure, and it's a stationary distribution. So this B, if you remember that if I replace X by T minus R, then the control, which is a feedback control, will depend on the previous state, right? So this is a very complicated stochastic differential equation. And what is the purpose of doing this? The purpose of doing this is try to find your admissible feedback control or the power control. To say assign at each node what kind of power, which means could be spectrum assignment, frequency of assignment. So that, and that depends on the channel condition as well as the Q size. So that this will be minimized. By minimizing this, you are minimizing what? The so-called total delay. Well, this delay means different things. The other delay means throughput, something to do with throughput or of the system. Okay. So this is another example of that why.
But you want to maximize the throughput.
You want to maximize throughput.
Yeah.
And you want to minimize delay. Right. And the one I show is minimize the delay. Okay. And the third example, which I didn't write any equation down, is something I have spent the couple months on, and just about four months ago, I didn't know anything about quantum physics, and there was this book I came across called Quantum Probability for Probabilities, and I said, yeah, I knew almost everything about probability, but this book has a strange title. It looks like I need to learn something new. So I went to the library and checked out the book. It's a Springer-Verlag lecture note in mathematics. And it turns out the quantum physicist has to do a lot of so-called non-commutative probability space. So I said, hey, this is interesting, and I spent a month pencil and paper and figure out from equation to another. So now I can say that I know something about it. Now, the probability space I have been working with for the last many years is a subset of this quantum probability space, which is non-commutative. And in the quantum physics, you work with the observable. Observable is some physical quantity, and usually is a linear operator on a quantum system, which is usually a finite dimensional or infinite dimensional Hilbert space. And there, for example, it's a finite dimensional space. The Hilbert space will be C to the n, which is complex, n complex variable, the space of that. Then the linear operator, those are self-adjoint, called observable. Observable could be in a quantum system, it could represent the position, it could represent the velocity or momentum. So electron is moving there, and each of those physical quantity is an observable. And it turns out this observable is a random variable. It's an operator value random variable. and they are not commutative, which means, for example, A is a matrix, random matrix, B is another random matrix. A times B is not equal to B times A. In quantum physics, if we say is commutative, which means the observable A and B can be realized in the same measurement, but in general it's not. For example, you cannot at the same time measure the velocity and the position at the same time. They may not be commutative, okay? And so, kind of historic, I got interested in that about 4 months ago. And then I look in the literature. There are people who work on so-called quantum filtering and quantum control. And there are some people who work on non-delay. So far, there's only one paper work with delay. They are deterministic, which this guy from Harvard is a young associate professor. It's a rising star, has done a lot of work. And non-delay stochastic one usually are done at Caltech. Okay. Again, in fact, this is a postdoc. This is just a PhD, and together with the advisor. Anyway, that particular project is also supported by ARO. So I start to read their paper, and I'm more or less interested in stochastic. Why stochastic? Stochastic because in a quantum system, every time for example, I want to see the status of an atom, okay, which is so tiny. How do you see the movement? How do you see the position? You use a laser beam to probe the state. But the quantum system has this problem. Every time you use a laser to probe it, it becomes a stochastic. It's called measurement back action. Okay, and it's a very interesting thing which I didn't know about, and I started to read the physics and all that. But one problem is if you want to know the state of these atoms or whatever, you need to use some kind of measurement. Like a laser beam. But when you measure them, it becomes random. So your observation is incomplete. And so there is filtering, nonlinear filtering, or if it's linear, in the classical sense, would be called Kalman filter that electrical engineers use a lot. But here would be a so-called quantum filtering. And then, based on the observation, which is a filter equation, then you want to do your control. And why do your control? For example, a physical chemist used to be that you have to introduce some kind of a compound, so-called catalyst, to induce the chemical reaction. So that you can have a desired final product. Nowadays, you don't do that. You use some external force like a laser to act on the compound, which are very tiny, narrow scale, and so that they will have a chemical to induce a chemical reaction. So, but you want to apply your control like a laser beam in a certain way, so that you will have a desired final state. Okay, so that's where the quantum control is. Now the delay, there's only one paper which just showed up in September. Why delay? Well, usually you know the filter state, which is after probing. But then you start to calculate what kind of control should I use. But the computational time for your control, feedback control, it takes time, even though you have a supercomputer and so forth, where the narrow dynamics of, for example, chemical interaction, they occur very fast in comparison with that. So whatever you see, the control C is you are using the old knowledge, which have a certain delay. And so that's where the delay comes in. And there's only one paper by these two guys just a couple months ago, and I'm working on the generalized equation. And you have to invent the new tools, mathematical tools, to solve this problem. But anyway, I didn't write any equation. But anyway, what is the problem I'm working on? The problem I'm working on is that I want to look at this. Look at this equation. Oh, by the way, I have two equations here. One is solved in our paper. The other one is not solved. What is not solved for the general case? The one is solved is that your control don't have delay. See, remember your subscript means the history, right? Now U of S is the current delay, which is solved in that paper for a general case. This is not solved. It's an open problem, and it's a very hard problem. Okay, I'm spending some time on it, but it takes time. It's a lot of things to learn, the delay control. All right, so again, that let me explain a little bit more. This term is called the drift term. Okay, and this is a diffusion term. And if diffusion coefficient G is identical to 0, then you are working with a deterministic control. Okay, and some people would write this as X star equal to F of this plus G W star. G W star is a white noise, but mathematicians don't usually do that. We look at it as a stochastic differential equation, and here that the second equation is not solved yet. And again, of course, a W is a Brownian motion. W star is a white noise. Okay. And F and G are called drift function, and G is a diffusion function. And drift function depends on the time, which is non-autonomous. Depends on the state. Remember, it depends on the state in this window. Right? And then you have a L2, which is a control function. And W is an m-dimensional Brownian motion. So G is n by m, and W is m by 1. So each term is an n-dimensional vector. Right? And so what is the problem? Well, the problem is I want to find a control process which take a value in certain control set. I want to apply the control. And of course, I'll explain a little bit more so that it does something. Okay. Now, again, I emphasize that this X sub S is the window, the history from negative S minus R to S. And if I have a U sub S, then that will be the control history up to time S. Okay? So this is another point where I want to emphasize. And for the first equation, I want to maximize this. There are two terms. This is expected value. The first term is a discounted reward per unit of time, and you integrate, that will be a total reward. And also, you will want to maximize the terminal term at the terminal time. This is a reward you get. And it's just like, each you get certain amount of money per unit of time from initial time t to the terminal time and go through that function. And at the end, you also be given a certain amount based on the state. And so this is the objective function you want to maximize by choosing appropriate control. This together with the equation 2 is not solved because of U sub S. Okay? So this is a very good, I don't think it's a good problem for a PhD student because you never know. You may stay there for 10 years trying to solve this. So you don't want you don't want a professional PhD student. So anyway, the value function is that if you apply the optimal control, which you usually use a U star as optimal. So if you have a optimal control, and if you are given the initial time and initial function, this is the value function. That is a function of initial time as well as the initial state. Okay, and this is called a value function. So the objective of an optimal control problem is to characterize this value function. Okay, and from there you can say, all right, from here can I find the optimal control U star? Usually yes, by one theorem called the verification theorem, which I'm not going to mention here. And again, that is just some standard condition on the drift term and diffusion term, some polynomial growth and so forth. So some regularity of the drift term and all that. And what is control? What is unusable control? You have to choose a probability space, you have to choose your Brownian motion, you choose your control process. So you have freedom. This is a so-called weak formulation. Strong formulation is that you have no choice of the probability space, you have no choice in Brownian motion. Here you, as far as expected value is concerned, it doesn't matter what kind of process you got, as long as they have the same expected value. So that's why you have choice of this. And U is a process that depends on, of course, the time as well as a random sample space, and is a F adapted. F adapted means that the control have a complete observation of whatever state that is. Okay, and so that the C value process. So remember here, X is output at the time S with the initial time T, initial function psi, and your input function. Right? It depends on three things: initial time, initial function, and your input control process. And then I look at the A sub S, which means I look at a window rather than the point in Rn. And so that this is a strong Markov. Okay, I don't want to spend. I don't think I should spend time getting into what is strong Markov, what is a regular Markov. But anyway, so these are the conditions. Now the correction of admissible control, which depends on probability space, the Brownian motion, and control, right? Which we call admissible control. And you want to find that, so that certain thing is, well, I already talked about the function you want to maximize. But since the time is running short, let me show you the equation, the infinite dimensional Hamilton-Jacobi equation. And again, there's a lot of notation. But here, remember you are working with the space function C, and you also, let me try to expand the space C into more general. Is the space of functions that are continuous everywhere except at the very right endpoint you might have a jump. Okay? And that space I will call C direct product with B, which is you have a function in C, and then you have some vector V times a function that is 0 everywhere except at the endpoint 1. And so this represents what? Represent the space of a function that are continuous everywhere except might have a jump at the right endpoint. Okay? So I look at, and again I have to as a mathematician, we always have to equip some space with a norm. And this is a norm, okay? I guess for engineer, you don't really worry about these things. You do, okay. Well, if you are doing mathematical aspect of problem, yeah, you do, yes. And let me kind of look at this differential operator. Remember, V is a function of initial time and initial function, right? And if you have a delay control, then you have an initial control function, which I didn't. I'm still working on it, and hopefully one of these days I'll get it. Is that this differential operator is a partial derivative with respect to t. Now this one is so-called infinitesimal generator of ship, of a semi-group of ship operator, which is very unique. It doesn't appear in stochastic PDE or anything else, just in this delay equation. It's a special type of operator. Now here, capital T is a Frechet derivative with respect to, remember the second argument is a function space. So you don't talk about regular partial derivative. However, if you see, if you don't look at the delay, you look at V as a function of Tx, then D might be gradient. Try to compare this with a gradient, right? Except here it's a Frechet derivative. And bar means you extend, it is a bounding linear operator on C, but you extend it to C plus B. And this one is a second order Frechet derivative. Now in the regular thing, in Rn you would say, all right, that is a Hessian matrix, right? The matrix of second order partial derivative. You try to imagine that is a special case. And then you extend it to C plus B cross C plus B. Remember a matrix, a Hessian matrix, you have a quadratic form, right? A vector times a matrix, and it's a scalar. And this is like that. And you have one half term. One half term is because of you are working with a diffusion, W, Brownian motion. Okay. So this differential operator. So if your value function is smooth enough, then you should satisfy this so-called infinite dimensional Hamilton-Jacobi-Bellman equation. Why we call infinite dimensional? Remember, this operator here involves Frechet derivative, not partial derivative. So this is the equation you want to solve. And without this max, it looks like linear, but with max, that make it a non-linear. So it depends on the parameter of initial control value, and you take the max, right? That make it very highly nonlinear. And so this is the equation we are interested in. How much time do I have?
I think you have maybe 5 minutes.
Okay, 5 minutes, okay. Now, so this is the equation we try to solve. Okay. And it turns out V, that the so-called value function cannot be a classical solution. When we say classical solution, means that V have a continuous partial derivative with respect to t, have a continuous Frechet derivative, and everything is continuous with respect to all its argument, and then satisfy the equation we call classical solution. But no, that the V at most is Lipschitz. It's continuous with respect to its time variable here. It's continuous with respect to initial condition in this way. We call Lipschitz condition. It may be a polynomial growth, but no way you cannot expect that V to be Frechet differentiable. All right, so that infinite dimensional Hilbert's SJB equation would not make sense because you cannot even take a Frechet derivative because we don't know, we are not sure that Frechet derivative even exists. And to cut the thing short, you have to really look at the weak solution. Okay, the weak solution means I cannot hope for that equation to have a strong classical solution. So the best I can hope for is a solution in a very weak sense. And when this weak sense, it is called viscosity solution. And what is a viscosity solution? We have to look at viscosity super solution, viscosity solution. If they are both, then it is a viscosity solution. So now let me look at the subsolution first. So instead of working with, or let me say W is your V, instead of looking at this directly, I look at the test function, right, gamma. So if there's a test function which is smooth enough, and they agree on one point, T psi, and with this condition that, or this is a test function is continuously differentiable with respect to time, and twice Frechet differentiable with respect to the space variable. So it's a very nice function. So if you have a test function that equal to each other at that point, then you have this inequality, not for V, but for the test function. Okay?
But typically a test function is just Schwartz. It's a Schwartz class function, right?
Yeah, it could be Schwartz class, which is can be differentiated in a weak sense. Right. Yeah, it could be that way, yes. And that happened a lot, even in the ordinary partial differential equation. And then the other way is super solution. Will be inequality go that way. So compared to the test function and the real function you are looking at, you have, they agree on that point. And in that point, if this is true, okay, then we call that gamma is a super solution. And if it is both a super solution and sub-solution, then we call viscosity solution. Okay. And let me just tell you what I got. It turns out that to show that the value function is viscosity solution, that's an easy part. 2-page proof. To show that it is unique, no other viscosity solution. This actually is about, that paper is about 35 pages. And we spent 21 pages proving uniqueness. Okay, and in fact, the first time we submitted,
they didn't want to review it.
they're not. Oh, it stayed there forever, and you know, see the problem with this kind of paper is that nobody don't know how to review it, and it stayed there forever. However, during the review, I say, hey, let me look at this again, and I say, hey, looks like there's a hole in it. So that was a Friday night. So I started to say, hey, I need to patch up this hole. And work on it for a long time. One day, I was in, during sleep, half sleep actually, because I keep thinking about this problem. I said, yeah, this will work. And so I immediately got up and write something down. And then the Sunday, okay, and I really try to type it up, and meanwhile doing the typing and so forth, and do a revision. And that take a long time to patch the hole. But anyway, we got this. Not only it is a viscosity solution, but also it is unique. Why uniqueness is so hard to prove? Remember, we are searching for weaker solutions. So your candidate has a lot of candidates you can choose from, right? And see, when you have a lot of candidates I can choose from, means it's harder to show that is the only one. And anytime you are working with a viscosity solution of some type, you always spend a lot more time trying to prove it is uniqueness. And as a mathematician, what's a big deal about uniqueness? Well, that's what we we do spend our time trying to prove everything without hole, and it's a 35 pages long paper, and we spend 21 pages on proof of uniqueness, which come from that comparison principle. And it looks like quite simple, right? You have a sub-solution, you have a super solution, and you say, oh yes, at every point in the domain, your sub-solution should be no bigger than super solution. I know that, but how do you prove it? Okay, and that's take a lot of work. Anyway, I better stop here, and if you have any questions.
Are there any questions? Questions?
You mentioned non-commutability, so that comes from a cross product somewhere in there, and that gives rise to the physical phenomenon that Einstein called spooky action at a distance, entangled photons, and so then that causes, at least on the surface, some people, spin up, spin down. When one changes, the other one's known to be on the other side of the universe, but instantaneously, seemingly. But then, if you read into it, and this is where kind of glossed over the details, but apparently you have to have some sort of verification, so you can't actually have superluminal communication, which is what the entangled thing would imply.
Yeah, entanglement. Yeah, that's it's a key.
So I don't know. What's your take on that? Like, make it make sense to me, if it's possible.
Okay. Yeah.
Most stuff just.
Yeah, that is over my head too, because I'm trained as a mathematician, and to confess that I hated physics. And you know why I hated physics? They make me do the lab. And where I came from in Taiwan, the physics lab is always on a Saturday afternoon. And I hated it. I hated it to begin with. And then they tell me to measure this and that. I say, isn't that equation already tell you why you need to measure it? So I would never make a experimentalist physicist, even a physics. But as far as a paper and thing is concerned, yeah, I don't know your answer. That is to do with the entanglement, has a lot to do with quantum information communication.
That comes out of the fact of the cross products, and once they're entangled, they stay entangled no matter what the distance, so changing one is reflected in the other.
Yeah, somebody had told me that. Somebody in ARO who managed quantum computing, he keep telling me that. Yeah, I don't know the answer. I need to read a lot more, but right now I'm more concentrating in quantum filtering and quantum control. Of course, I see those researchers who spend on a small area in their lifetime, and I guess that's what people would do. I don't know anything about.
They also have those guys. That's fairly recent. I think it's in Germany. Those guys, the silly Germans, they want to say that you can get superluminal communication at the evanescence. So you have total internal reflection. A prism, or this isn't a good prism. So if you took a square, that's not really a square, but anyway, so these now are split apart. You have two prisms, and total internal reflection here. It jumps across and continues here through the evanescence, which is the equivalent of quantum mechanical tunneling, but with optical, with light. Yeah. And so at least from here to here, they're claiming that they get faster than light communication, but then other people get into this, that's not signal velocity, that's on top of the carrier frequency, that's phase velocity, is counts, you can't transmit information. So they'll say within a medium you can do faster than the native medium transfer speed, but not actually faster than light. But then I think that's what they're claiming that they can do.
I see.
But I don't. Yeah. So those are two cases where they claim where it's suggested that maybe there's faster than light and stuff, but then they say it's not really faster than light. Yeah. So, because otherwise Einstein would be really mad. He'd roll over in his grave. All that.
I have a question though. Actually, we have looked with some of my students. We've looked at these nonlinear stochastic differential equations in context of nonlinear filtering in imaging, actually. Right. Have you guys looked at problems of that nature?
Oh yeah. In fact, one of my Mou-Hsiung, now current Mou-Hsiung, led by Boris Wozowski, who has, well, he's a prime mathematician, but anyway, one of the guy in that Mou-Hsiung, everybody doing non-linear filtering with a focus of counterterrorism and information assurance, and one of the components about that the image. In fact, I myself have written a paper long ago, 81. It's called Image Restoration using delay equation, stochastic. Yeah. You see, you have an observation, which is what you got, right. Image, and you have a real image. You have a noise and blur it, and then what you want is you know the information of observation. You want to see what is a real signal, real image. Exactly. Yeah, that can be done using the nonlinear.
Yeah, maybe you should talk, because actually we have some papers on that where we look at pixels or images as particles.
Right.
Sort of in a microscopic state of a particle system.
Right.
And then we derive nonlinear filters based on that.
Yeah, nonlinear filtering, of course, if it's continuous case, you look at a Zakai equation. Now, for delay, nonlinear filtering for delay, there were so far only about 4 papers.
Yes, it's a very difficult problem.
Yeah.
Yeah, we ran into that problem.
Yeah. One is Aaron Wilsky, which is a linear. The second paper is 86, done by me. Then there's a big name called Karyampo in UNC. He had an O2 paper with one of his former students. And now there's a group of German mathematicians from Hamburg University, and he do the numerical computation. And then the other day appeared in Science, and he said, as far as he knows, there were only 3 papers, and my paper was in there, and that my paper was about 20 years ago. I quit. I said, hey, let somebody else worry about it. Now he was comparing his result with mine, which is already 20 years old.
Actually, there's a very bright. In fact, I'm pretty sure he works with a colleague and a friend of mine from Russia.
Yeah.
There's a very bright Russian mathematician, 40 years old, 45 years old, very young.
Yeah.
And who's doing some very interesting work also.
Okay, I would like to see that.
Yeah, we can talk about it. Yeah.
Okay.
Well, if there are no more questions, let's thank our speaker again.